Welcome to AI Paper Slop, our YouTube series where we summarize the latest AI and tech papers. Today we are looking at a paper from Meta and Princeton University titled Vision Language Models Are Native 3D Learners, and we're just going to dive straight into the core insight.
Yeah, let's get right into it.
Because this completely flips the script on how we handle computer vision. For years, the consensus for you ML engineers out there has been that if you want a model to understand fine-grained 3D space, so things like exact depth estimation or calculating a camera's physical pose, you have to build a heavily engineered expert vision model.
Right, which means tons of specialized architecture.
Exactly. Multi-head architectures, really complex, regression losses, incredibly heavy image augmentations. But this paper proves that approaches, well, it's entirely unnecessary.
It really is.
The researchers took a standard 4 billion parameter vision language model, specifically Qwen3 VL4B, applied standard text-based supervised fine-tuning, made literally zero architectural changes, and managed to match or beat those dedicated expert vision models.
Which is just wild to think about.
And the secret sauce is just 3 really straightforward formatting tricks. Unifying all image focal lengths to 1,000 pixels, normalizing text-based pixel coordinates to a fixed 0 to 2000 scale, and applying a highly specific dataset mixture weighting.
What's fascinating here is how thoroughly this dismantles the current machine learning paradigm. I mean, we have treated 3D vision as this rigidly distinct, highly specialized subfield, totally isolated from natural language processing.
Yeah, completely siloed.
Right. The operating assumption was always that standard next token prediction models, they just lacked the inherent spatial intuition to understand geometry.
Like they literally couldn't comprehend 3D space.
Exactly. Therefore, we had to force feed them that intuition through really heavy inductive architectural biases.
I want to focus on that status quo for a moment, actually, because for the AI researchers tuning in, you are intimately familiar with the pain of building these systems.
Oh, definitely. It's a headache.
But let's break down the mechanics of what a typical expert vision model actually requires under the hood, just so we can contrast it with what VLM3 is doing here.
Well, it generally looks like a messy soup of complex structural add-ons. Like if you build a standard 3D vision model today, usually start with a pre-trained vision encoder, right? Which compresses your image into a low-resolution latent space.
Right.
But to get fine-grained 3D predictions out of that, you have to reconstruct a high-resolution spatial map from those highly compressed features.
Which is where it gets messy.
Super messy. That requires bolting on task-specific routing mechanisms and multiple dense decoders. Typically, you're looking at FPNs, which are feature pyramid networks, or DPT decoders.
And if you're trying to solve a task like pixel correspondence across 2 totally different images, you can't just rely on the raw embeddings either.
No, not at all.
You have to engineer these intense multi-scale warping operations just to force the model to find accurate physical matches.
And because you're bolting on all these different prediction heads for all these different tasks, you inevitably create an absolute nightmare in the loss landscape.
Yeah, the loss landscape just becomes a minefield.
That is the real bottleneck. When you have multiple specialized prediction heads, you are juggling multiple competing loss functions.
Right.
You might be using mean squared error for one head, L1 for another, maybe a clipped L2 loss elsewhere, plus certainty losses, or even framing regression as a classification problem.
It turns training into this incredibly fragile balancing act. Like, if the depth estimation head learns faster than the camera pose head, your gradients can just explode.
Or collapse completely. You end up spending weeks just tuning hyperparameter weights to keep the model stable. And that's not even mentioning the heavy photometric and geometric data augmentations you have to write.
Just to make the model robust to like different lighting or camera angles.
Exactly.
And the prior literature trying to bridge this gap with vision language models didn't do much better, frankly. They were mostly relying on these really weird physical hacks.
Yeah, some of the workarounds are pretty clunky.
Like, look at something like spatial RGPT. That required entirely separate custom encoders just to process object masks alongside the text.
Right.
Or the Depth LM paper, their solution was to literally render colored visual markers onto the input images before passing them to the VLM.
Literally drawing on the image.
Just so the model had a visual anchor for the pixel they were asking about. It's essentially the ML equivalent of building an incredibly complicated, highly calibrated, multi-attachment power tool to drive a single nail.
That's a great analogy, actually.
And then this VLM3 paper comes along and proves you could have just used the factory issue hammer that was sitting on the workbench the whole time.
Yeah, exactly.
Which brings us to the core technical mystery here. How does a model train strictly to predict the next text token process physical 3D space without any regression loss? Let's get into the mechanics of their three ingredients, starting with focal length unification.
So to understand this fix, you really have to understand the camera ambiguity problem first. A camera matrix translates 3D world coordinates, so your x, y, and depth z, into a 2D pixel grid.
Right.
And it does this by dividing by the depth and multiplying by the focal length. The problem is, if I hand an image encoder a 2D photo without providing the camera's internal hardware specs, the intrinsics, that equation has two missing variables.
Right, it's the classic toy car ambiguity.
Exactly.
If I hold a miniature toy car 2 inches from the lens, the pixels might look completely identical to a real full-size car parked 50 feet away. To the vision encoder, 50 pixels of car is just 50 pixels of car.
And that geometric ambiguity is exactly what usually forces researchers to build separate camera encoders to feed those intrinsics into the network. But the VLM3 team, they just bypass it entirely with a really simple geometric trick.
Oh, I love this part.
They take every single input image in their training data and resize the resolution so that the simulated focal length becomes exactly 1,000 pixels.
You just lock the variable.
They lock it. By artificially standardizing the focal length to 1,000 across the entire dataset, they lock that previously unknown variable in the camera matrix.
Yep.
So they create this universal standardized mapping of pixel distance to real-world depth.
So the neural network no longer has to guess the camera hardware at all.
Nope. It just natively learns that unified mathematical relationship.
But, I mean, there's an obvious practical limitation here, right? If you are scraping wild, unstructured data sets off the internet, you don't have the EXIF data or the camera intrinsics.
True.
You don't know the original focal length, which means mathematically you don't know how much to resize the image to hit that magic 1,000 pixel mark.
Which is a very real constraint for scaling. But their solution is to run a lightweight, pre-trained single-image calibration model over the wild data first.
Okay.
That model estimates the intrinsics, and then they use that estimation to unify the focal length, so it adds a small pre-processing step, but it completely standardizes the metric scale for the VLM. It allows it to process wild internet data seamlessly without altering its core architecture.
Okay, let's unpack this, because ingredient number 2 is where the paper makes its biggest leap, and I really want to push back on it based on what previous researchers claimed.
Sure, let's hear it.
You brought up the DepthLM paper earlier, and they explicitly concluded that VLMs cannot understand text-based pixel references. If you prompted their model with text asking, how far away is the object at pixel coordinates, x equals 500, y equals 300, the model just hallucinated.
It completely broke down, yeah.
The positional embeddings completely failed to map the text numbers to the visual features, which is exactly why they had to physically draw those colored markers on the images. So how does VLM3 suddenly make text coordinates work perfectly?
Well, the failure of previous models wasn't a lack of spatial capability. It was actually a tokenization and mapping failure caused by raw image dimensions.
Okay, how so?
Think about the chaotic token space you create if you use raw pixels. In an image that is 800 by 600, the coordinate x equals 400 is dead center.
Right.
But in an image that is 1920 by 1080, x equals 400 is way off to the left side.
Oh, I see. So the LLM's positional embedding for the text token 400 is just constantly being pulled in different directions during training.
Exactly. It represents the center of the room in one sample and then the left wall in another.
That chaotic variation prevents the LLM from building a consistent internal geometric representation.
Precisely. So to solve this, VLM3 strips away the native resolution entirely. They normalize the pixel space.
Right.
Regardless of whether the original image is a tiny square Polaroid or a massive ultra-wide billboard, both the horizontal x-axis and the vertical y-axis are mathematically normalized to a continuous range starting at 0 and ending at exactly 2000.
Think of it like laying a transparent piece of standard graph paper over every single photo in the dataset.
Yes, perfect analogy.
The bottom right corner is always coordinate 2000, 2000. The center is always 1000, 1000. Suddenly, the LLM isn't dealing with wild shifting dimensions anymore. It just memorizes the fixed graph paper.
That is the precise mechanism. Because the text tokens for the coordinates now represent an absolute unchanging position in that normalized space, the positional embeddings of the language model can easily map that fixed 0 to 2000 range to the corresponding visual tokens output by the encoder.
So you can ask it, what is the depth at 1500, 1500, and it inherently knows exactly where to look. No visual markers necessary.
None at all.
And by stripping away those physical visual markers, they unlock the third ingredient, which is pure compute efficiency through data scaling.
Yeah, this completely removes the major compute bottleneck in the pipeline. With models like DepthLM, if you wanted to query the depth of 10 different pixels in a single image, you had to physically render 10 separate images, each with a marker in a different spot.
Meaning you have to pass those 10 distinct image variants through a massive, computationally expensive vision encoder 10 separate times.
Which is incredibly slow.
Mm-hmm.
But because VLM3 uses normalized text coordinates, the input image remains completely clean. You pass the image through the vision encoder exactly once.
Oh, wow.
Then you just stack multiple text questions into the prompt for that single visual pass. In their training pipeline, they routinely packed 10 question and answer pairs representing 10 different labeled pixels into every single image sample.
I was actually looking at the compute math on this, and it is a massive disparity.
It's crazy, right?
The DepthLM paper required 128 H100 GPUs running for 2 full days just to train a 3 billion parameter model. The VLM3 team, entirely because they can pack 10 QAs into a single encoder pass, trained a larger 4 billion parameter model using just 32 GPUs over 3 days.
Yeah, and they did it while chewing through significantly more data, too.
It totally democratizes the research space. You no longer need an exorbitant compute budget just to experiment with fine-grained 3D representations.
Exactly.
But compute efficiency is meaningless if the model's outputs are garbage. The real test is applying this setup to the actual benchmarking tasks. And they tested VLM3 across 4 drastically different 3D problems to prove this isn't just a, theoretical formatting trick. Let's start with metric depth estimation.
Sure. Metric depth estimation is exactly what it sounds like. It's predicting the absolute physical distance of objects from the camera. The standard metric here is delta-1 accuracy, which essentially measures the percentage of predicted pixels that fall within a strict acceptable margin of error compared to the true depth.
And the 4 billion parameter VLM3 model bumped the delta-1 accuracy up from 0.84, which was the prior state-of-the-art held by the 7 billion parameter DepthLM, up to an impressive 0.90.
That's a huge jump.
It matched highly specialized, deeply engineered expert models like Unidepth V2, despite being a general text model, and it carried that performance over to object-level 3D tasks, too.
Yeah, it beat models like spatial RGPT-8b on spatial reasoning.
Right, figuring out horizontal distances and bounding box dimensions, and again, it used pure text coordinates without any dedicated bounding box encoders.
Then they moved to multi-view tasks, which is where the structural lack of complex multi-scale warping really gets tested. Take pixel correspondence, for instance.
For context for our listeners, imagine trying to code a system that tracks a specific white coffee mug sitting on a desk. Camera A is mounted in the top left corner of the room, and camera B is mounted on the opposite ceiling, looking at the desk from a completely different angle and lighting condition.
Right.
The task is to pick the pixel on the mug in camera A and force the model to find the exact same physical point on the mug in camera B. It's notoriously annoying to solve.
Historically, yes, very annoying. Expert models rely heavily on feature matching algorithms and spatial warping to align the geometries of the two different views. But VLM3 takes the two images, applies the focal length unification, lays down that normalized 0 to 2000 text grid, and you just prompt it with the coordinate.
And the result is measured in endpoint error, or EPE, right?
Yep, EPE, which calculates the pixel distance between the model's guess and the true location. VLM3 reduced the EPE by a factor of 10 compared to its base Quinn 3 model.
A factor of 10.
And critically, it outperformed dedicated correspondence expert models like DKM and Roma.
Here's where it gets really interesting, though. Task number 4, camera pose estimation. I was reading these benchmarks, and frankly, I had to double-check the tables.
It's hard to believe at first.
The premise is that you feed the VLM 2 images from different viewpoints, and you prompt it to output the exact movement the camera made between shot A and shot B.
And the output required here is mathematically rigorous. The model is prompted to generate the translation distance in absolute meters, the translation direction as a precise unit 3D vector, and the camera rotation expressed in exact degrees of yaw, pitch, and roll.
It is literally just generating text that says, translation distance, 1.75 meters, direction vector XYZ, yaw equals 8.8 degrees, pitch equals negative 13.9 degrees. Like, how does standardizing text coordinates suddenly turn an LLM into a trigonometry engine capable of writing out the calculus of a moving camera?
It works because next token prediction is ultimately just highly advanced pattern recognition across an embedded space. By unifying the focal length and normalizing the grid, the model no longer has to expend parameter capacity trying to guess the fluctuating spatial rules of the images.
It doesn't have to fight the formatting.
Exactly. It just maps the geometric transformations between view A and view B directly to the text tokens representing degrees and vectors.
And the performance leap is what really caught my eye. If you ask the raw base Qwen 4B model to do this, its AUC at 30 degrees, which measures the area under the curve for rotation predictions that are accurate within a 30-degree window, is a dismal 5.4%.
Yeah, it's basically guessing at that point.
But apply the VLM3 methodology and that accuracy rockets to 94.0%.
Incredible.
Going from 5.4% to 94% just by formatting the data correctly and fine-tuning, it matches state-of-the-art pose estimation pipelines like DA3 Giant entirely without optimization solvers or point tracking over time.
It treats complex 3D geometry as just another language to translate.
Which naturally leads us to the training dynamics in section 4 of the paper. Because to teach the model that language, the dataset construction has to be flawless. And for the ML engineers listening who are constantly wrestling with dataset scaling, the findings here expose some deeply counterintuitive realities about scaling laws.
If we connect this to the bigger picture, the researchers ran headfirst into the overfitting trap. They initially hypothesized that simply scaling up their training dataset from 8 million samples to 32 million samples would unilaterally improve performance.
As you normally would assume.
Right. But when they scaled up using uniform mixture weights, meaning they sampled equally across all their data sources, the performance actually got worse.
Which completely violates the golden rule of the current AI meta, right? More data is supposed to equal better generalization.
Only if the data distribution is balanced. In 3D vision, datasets vary wildly in both volume and complexity. You might pull millions of samples from a dataset composed of highly repetitive, really simple synthetic indoor scenes.
Like perfectly lit CAD models.
Exactly. Meanwhile, your dataset of incredibly complex, real-world outdoor environments might only contain a few thousand images. If you sample them uniformly, your high-capacity model will see those complex real-world scenes so frequently that it rapidly overfits.
Ah, I see.
It essentially memorizes the specific visual textures of the small data set, which destroys its ability to generalize the underlying geometric principles to new images. To hit that 0.90 state-of-the-art mark, the team had to mathematically weight the data sets based on their relative sizes and apply heavy custom penalizations to the smaller data sets that were prone to overfitting.
And that overfitting dynamic explains a major pushback I had while reading the paper, The Small Model Paradox. They found that scaling the model's parameter count actually hurt the performance.
Yeah, that was a huge finding.
They fine-tuned a massive 32 billion parameter version of Qwen 3, assuming it would crush the smaller version. Instead, the 32B model scored a 0.873 on depth estimation, which is noticeably lower than the 4 billion parameter model's 0.904. And even when they took the smaller 4B model and just trained it for longer, pushing it to 64 million samples instead of 32 million, the accuracy dropped again.
This is such a critical lesson regarding the curse of dimensionality in the parameter space. For the engineers listening who are begging their managers for more H100s to scale their model parameters, this paper is a warning. At the specific scale of this experiment, which was about 26 million unique images, a 32 billion parameter model is basically acting like a photographic memory.
Just rote memorization.
Right. 26 million images sounds vast, but for 32 billion parameters, it is a tiny lookup table. The model has so much spare capacity that it doesn't bother learning a generalized mathematical function for 3D geometry. Instead, it just rapidly memorizes the idiosyncrasies of the training set.
So the smaller 4 billion parameter model is actually forced to be smarter. Because it lacks the capacity to just memorize 26 million images, it is forced to compress the information by actually learning the underlying geometric rules.
Precisely. It proves that throwing a larger model or more raw compute at a problem before you have painstakingly optimized your data representations and mixture distributions, well, it's a fast track to failure. At this data scale, mixture quality absolutely trumps parameter count.
So what does this all mean for the future of the field? If we synthesize this analysis of the source material, VLM3 proves definitively that the era of treating 3D vision as a uniquely rigid domain might be over. Task-specific architectural designs, heavy image augmentations, and those delicate, endlessly tuned regression losses are not strictly necessary for fine-grained 3D tasks.
They really aren't.
A standard vision language model architecture relying solely on autoregressive next token prediction is remarkably versatile. As long as you solve the camera ambiguity by mathematically unifying the focal length, normalize your input space so the positional embeddings can actually understand the coordinates, and strictly balance your data mixture, the model will learn to output complex 3D space natively in pure text.
And for the practitioners building these systems, let this be a call to simplify your pipelines. Before you start building a complex multi-head architecture with custom loss functions and specialized feature extractors, take a step back.
Look at the data first.
Exactly. Ask yourself if the physical data representation you are working with can be cleanly translated into a normalized, predictable text format. If you can format the environment in a way that a foundational language model can mathematically digest without contradictions, the model's innate pattern recognition might just do all the heavy lifting for you.
That is a phenomenal takeaway. And I want to leave you with a final provocative thought to mull over as we wrap up. If simple next token prediction can natively master fine-grained multi-view 3D geometry, literally predicting camera roll and pitch to the decimal point without any specialized physics engines or inductive biases, what else is out there?
That's the real question.
Think about other rigidly specialized fields like robotics, kinematics, complex physics simulations, or even fluid dynamics. Are those fields really as complex and specialized as we think they are? Or are they just waiting to be completely solved by a standard, off-the-shelf LLM using the exact rate data normalization? It's something to think about the next time you assume a problem requires a custom architecture. Thanks for joining us on this dive into VLM3 here on AI Paper Swap. Keep questioning the architectures, and we'll see you on the next one.